All right, welcome everybody to the CUTLASS talk for GTC 2024. If you are not familiar with what CUTLASS is, I'll give you a quick rundown. CUTLASS is a C++ template library for linear algebra subroutines that is very frequently used in deep learning and HPC domains. It decomposes tensor computation at all levels along the moving parts and across a conceptual hierarchy such that you can target it at various levels. CUTLASS is open source. It's available on GitHub. And we have a vibrant community and 2.5 million downloads a month at this point. We have hundreds of contributors, and you're welcome to engage with us in issues and discussions over there. We're presented at every GTC since 2018 before, and you can find our prior slides over there. And every GTC, we end up presenting what's new and what's been happening in CUTLASS within the past year. This year, we have 3 main topics to cover. First is convolution support in CUTLASS 3 API. Second is dedicated optimization and features we've implemented for large language model optimizations. And lastly, the third thing is flexible fusion support via epilogue visitor trees. But before I go into the main topics for today, I just wanted to highlight some of the other minor topics that we don't have the time to dive into the details of, but we would like to highlight. In the last year, CUTLASS has added FP8 support across Ada and Hopper. CUDA 12.4 exposes the PTX instructions for Ada, and they are now exposed in CUTLASS 2 as of last night with the CUTLASS 3.5 release. We've also greatly improved our Python support and have a native PyPy wheel that you can download and use directly. Since the release of CUTLASS 3, we've also implemented composable schedulers for our kernel levels for flexible load balancing strategies so that you can implement custom kernels or reuse our schedulers for things like StreamK. And lastly, we've expanded our compiler support for host compilation using MSVC and Clang. We've implemented narrow alignment gems so that in cases where you can't use TMA, we can fall back to CP async instructions. And we've greatly improved our documentation, especially for Qt within the last year. So with that out of the way, let's dive right into the details of how convolutions are implemented in CUTLASS 3. So as a reminder for what CUTLASS 3 is, if you are not familiar with the hierarchy of how CUTLASS 3 is structured, it's split into 5 levels within its conceptual hierarchy. At the very foundational level of CUTLASS 3 is Qt, and it encompasses 2 of the conceptual levels. At the very foundation of this, we have the atom layer, which are architecture instructions and their associated metadata expressed as Qt layouts, so that we can have a uniform representation, regardless of which architecture it is, of the math and copy operations that are native on the hardware. On top of this, we build an abstraction that we like to call the spatial microkernel layer. That maps onto the Qt tiled MMA and tiled copy. And they are intended to describe a complete spatial tiling of arbitrary math and copy operations within the atom layer. On top of this, CUTLASS builds a temporal microkernel hierarchy, which describes the complete synchronization and K-loop tiling of these spatial microkernels using architecture-specific synchronization primitives. On top of the collectives are the familiar CUTLASS 2 and CUTLASS 3 kernel layer and device layers that do all of the grid scheduling, load balancing, arguments construction, and kernel launch, etc. In CUTLASS 3, we've made a great effort to flatten the learning curve. And as a result, we have greatly reduced the API surface area such that there's only one entry point for each of the 5 conceptual layers that are presented above. And you can see them over here. And the key thing that I wanted to highlight today with this slide is that convolution fits beautifully into this hierarchy, despite us not having discussed convolutions whatsoever and only having spoken about gems. If you're familiar with the CUTLASS 3 gem hierarchy, the temporal microkernels are referred to as the collectives over there. And we had collective MMAs until now, until the 3.5 release. And with the release of 3.5 yesterday night, we have convolution collectives as well. And they're very similar in both their API as well as the usage model to the gem collectives, except that they implement a convolution algorithm. So just like the gem API, the convolution collectives are dispatched against via main loop policies. They compute a single output tile, and they're intended to compose with arbitrary kernel scheduling strategies if you have custom kernels, or in our case, we have provided you with convolution kernels so that you can use them off the shelf if you just wanted a kernel level operator. Almost all of the convolution-specific changes in 3.x are limited to this main loop, or what we call the collective, right? So this collective implements the actual convolution algorithm, be it fprop, dgrad, or wgrad. It maps the input tensors to Qt strides and Qt shapes, and it constructs, in the case of Hopper, the IM2call TMA instruction-related descriptor, et cetera, so that we can actually take advantage of Hopper instructions. The CUTLASS collectives for convolutions are completely composable with the epilogues that we have had so far. And what that means is at the kernel layer, it's still a composition of a main loop and an epilogue is none the wiser that it's a convolution that's being implemented. And that gives you out-of-the-box day zero support for any custom epilogue that you might have written or the epilogue visitor tree that Jack will talk about later. Of course, just like GEMS, we also ship this convolution API with a convenient builder API that is intended to make it much easier for you to implement convolutions off the shelf. So what we do with the builders is we give you a API that is architecture agnostic and just allows you to stamp out kernels. So in this case, let's say I just want a Hopper fprop collective for a 1D spatial dimension convolution. And in that case, all you have to do is pass in your input data types, in this case FP16, tags for your input layouts, your alignments, and just leave everything else to auto. You don't need to worry about the kernel stage count. You don't need to worry about which kernel policy. Just define your tile shapes and your architecture number, SM90 in this case, and voila, you end up with a collective. Of course, one of the philosophies of CUTLASS 3 is incremental opt-ins for optimization and customization. So let's say I want to slightly modify this and take control over it so that I can dedicate some shared memory for some other collective I might be fusing this operation with. In that case, I need to reduce the number of stage count so that I can set aside shared memory. And let's say I want to implement a 3D dgrad in this case with 5 stages. Then I leave everything else the same, use tags for 3 spatial dimensional tensors, and set my stage count to be 5. And that will stamp out the collective using the same builder. And the builders are doing a lot for you behind the scenes, right? So this is the same builder argument for the dgrad from the previous slide, but what the builder is doing is a meta program that actually computes the main loop type to dispatch against. It computes the stage count to make most use of shared memory. It picks the WGMMA instruction for Hopper. It picks the TMA instruction as well as which ones to multicast against, et cetera, et cetera. And all of that is listed over here. So that's what the builder is generating via its meta programs. And of course, the collectives still remain our primary API for an expert user. If you want full control, you're welcome to use the collective API directly. But the builders are there as a convenience. All of this maps onto a very familiar flow. The first thing you do for a convolution kernel is stamp out your epilogue. Then you stamp out your main loop collective. Then you compose them together at the kernel level. Each kernel is a composition of multiple collectives, in this case, a main loop for the convolution and a main loop for the epilogue. And then that's it. You have a convolution kernel. All of this is completely symmetric with the GEM API. So let's look at how some of these things are implemented within the 3.x API. We don't have time for a full deep dive, but we'll go over some of the things. One of the things that we wanted to do in CUTLASS 3 is implement convolutions in a way that is agnostic to the spatial dimensions. In CUTLASS 2, we only had 2D and 3D convolutions. With CUTLASS 3, we wanted to support arbitrary spatial dimensions. For now, we have 1, 2, and 3D spatial dimensions, but they're implemented in a way that is extensible to 4, 5, or arbitrary number. And that's the first challenge in doing that is representing these problem shapes for convolutions in a way that doesn't specifically name modes and is rank agnostic instead. And we do that with a new problem shape type that is user-facing, which only depends on the number of spatial dimensions and the convolution operator that's being implemented. And you can see how some of the arguments are filled in for a 3-dimensional convolution problem over here. This also leaves the IM2call transformation that is used for the implementation of convolution algorithms as an implementation detail. The problem shape tab will take care of mapping asymmetric padding, dilations, traversal strides, et cetera, onto this domain transformation that is required for implementing this convolution so that you never have to worry about it yourself. The problem shape will take care of that. But then, I just told you, all of CUTLASS 3 is implemented using Qt, and it has a layout representation that is natively hierarchical and multimodal. So how do we map this flat problem shape to Qt shapes and strides? Well, in CUTLASS 2 days, we would have done this via layout tags, right? But these are not composable with the Qt layout algebra that we have, and we would really like to do this in a way that doesn't have to name modes and make it rank agnostic. But if you remember our talk from last year, the power of hierarchical layouts in Qt is that we can turn almost every linear algebra problem into a batch tensor contraction, right? And we can do so by folding multiple nested dimensions of tensors into their logical modes that correspond to either the row, column, reduction, or batch, such that every problem turns into a hierarchical rank 3 stride with possible multimodes within it. And the core observation to make with convolution is that convolution is just a specialization of a tensor contraction, which we would normally refer to as jets, right? The IM to call transform is a transformation that we apply to the shapes and strides of the activation tensor that turns the problem from a convolution to an implicit gem. And after this transformation that takes into account the filter, dilation, traversal strides, and any kind of padding, we can make sure that the M dimension of the activation tensor is a multimode that is logically consistent with the output matrix, and the K multimode of the activation tensor is consistent with the filter dimension TRS. And then that's it. We have transformed our problem using IM to call transformations into a tensor contraction. And this is exactly why we don't need the full generality in the convolution problem shape, because it turns out convolutions are just a special case of contractions. Hopper IM to call TMA makes this extremely easy and convenient to implement as well. If you have ever implemented IM to call transformations and implicit gem in SIMT kernels, you will realize that it's really hard to do because of all the complicated predication that is required and the replication of input tensors and accounting for the halos and paddings, et cetera, right? But IM to call makes this super easy by taking care of mapping the IM to call transform onto the strides itself within hardware. It also does the predication for out-of-bounds reads of the tensors so that you don't have to do predicate-related things. And it greatly reduces the issue overhead of these instructions, as well as reducing the address computation register pressure required, right? So it greatly accelerates the data loading for convolution tensors. So in summary, what we have in CUTLASS 3.5 with the initial release is a beta API. Feedback is very welcome. Please tell us if you like it, you hate it. And for now, we support 1, 2, and 3 spatial dimensions in a rank-agnostic manner. FPROP, DGRAD, and WGRAD are supported out of the box with asymmetric padding, dilation, and traversal strides. And there's some initial profile integration for 2D and 3D convolutions. For the roadmap, we're going to greatly improve performance in the next few releases, implement strided DGRAD, and extend profiler coverage to one-dimensional as well. And now I'll hand it over to Jack Kosayan to take over for the LLM portion.
All right. Can you all hear me all right? Good. Great. So since the last CUTLASS GTC talk, large language models have become an increasingly popular workload. To better suit these applications, CUTLASS has been enhanced in a number of ways. In this part of the talk, I'm just going to describe 2 of these, which is how CUTLASS's group gem optimizes mixture of experts models, and second, how CUTLASS's mixed input gem enables generic weight quantization for LLMs. To begin, we'll describe how CUTLASS's group gem optimizes mixture of experts models. For a little bit of background, the goal of a mixture of experts model is to be able to efficiently scale the parameter count of a model without a correspondingly large increase in compute cost. To do so, a mixture of experts model adds parameters to the model via distinct experts. Inputs to the model will first pass through a gating network that determines to which experts it should be routed. For example, input 1 might be routed only to experts 0 and 2, and another input might be routed only to experts 1, 2, and 3. Through the gating network being selective about which experts it's going to consult, we can continue to add new parameters to this model via an increasing number of experts while keeping compute costs low because we're not going to consult every expert for every input. Under the hood, each of these experts is computing at a minimum a gem. Thus, we could overall view this workload as one in which we'd like to run multiple gems in parallel, but in which the size of each gem is potentially different from one another. And finally, in which the number of gems that we're going to compute for each input may differ with every input. So at a first glance, you might wonder whether something like a batch gem is a good fit for this workload. Unfortunately, however, batch gems assume that every gem is going to be computed for every input and that the size of each gem will be the same. In contrast, CUTLASS's group gem is a good fit for this type of workload. Group gem involves computing multiple gems concurrently within a single kernel, in which each gem can have a distinct shape and stride from one another. And finally, in which the number of gems and their parameters don't need to be known at compile time. They can change with every input that you pass in. Thus, group gem is a good fit for a mixture of experts model. So to better illustrate some of the benefits of CUTLASS's group gem, I want to walk through a relatively simple example. So suppose that we had 3 gems that we'd like to compute in a group. And what I'm showing here are the tiled output sizes for each gem. What I mean by this is that each individual box with a number in it represents the result from a single thread block, or CTA as you might refer to them. To illustrate the benefits of group gem, I first want to show what would happen if we were to execute these gems serially on a set of 8 CTAs. So we'd begin by executing gem 0 by assigning its 4 output tiles to CTAs 0 through 3. However, CTAs 4 through 7 would remain idle. Once this is complete, we'd next execute gem 1 by assigning its 6 output tiles to CTAs 0 through 5, but the final 2 CTAs would be idle, and we'd see something similar for gem 2. Overall, it's pretty easy to see the downside of this approach. Under serial execution, some of our CTAs will remain idle. It would be great if instead we could make use of these CTAs to compute useful work for other gems in our group. And this is exactly what CUTLASS's group gem attempts to do. Rather than considering a single gem at a time, it instead considers all of the output tiles across all the gems in the group within a single kernel launch and schedules them over a set of persistent CTAs. So, for example, CTAs 0 through 3 will continue to compute the 4 output tiles for gem 0. But now, rather than sitting idle, CTAs 4 through 7 will begin computing the first 4 output tiles of gem 1. We then loop back around to CTAs 0 and 1, which will compute the final 2 output tiles of gem 1 once they've finished their first output tiles. And then finally, we'd assign the output tiles for gem 2 to the remaining CTAs. All of this work is computed within a single kernel launch over a set of persistent CTAs. That is, we don't launch a new CTA for every output tile, but instead launch just enough CTAs to saturate our GPU and potentially assign to each of them multiple tiles to compute. Now, the benefits of group gem are the following. First, it allows us to potentially saturate the GPU via multiple small problem sizes that in isolation would be unlikely to make good use of the chip. Second, we do all this work in a single kernel launch, which means that we don't have to pay additional kernel launch overhead from running these in separate kernels and don't need to deal with distinct CUDA streams in an attempt to parallelize this. Using a group gem in Hopper, in CUTLASS 3 is really straightforward. One can continue to use the same collective main loop and collective epilogue builders that Vijay described earlier in this talk. All that needs to change is that one should represent the layouts for A, B, C, and D using pointers rather than distinct tags like row major and column major. Under the hood, CUTLASS's collective epilogue or collective builders will take care of dispatching to the correct kernel policies. Now, we've made a number of optimizations to group gem for Hopper. Here I want to describe just one of these features because it relates to a new feature within the CUDA toolkit. And this specifically relates to how we represent TMA descriptors in Hopper group gem. So recall that Hopper's Tensor Memory Accelerator, or TMA for short, requires making use of what are known as TMA descriptors when performing copies. These TMA descriptors encode useful information that's going to be needed for the copy, like the global address, global stride, etc. Within a single gem kernel, we simply needed to represent enough TMA descriptors for each of operand A, B, C, etc. And each of these TMA descriptors would just be used throughout the lifetime of the kernel because we only had one gem to compute, so we only had one operand A. In contrast, group gem looks a little bit different. We have potentially many gems that we'd like to compute, and so for each of those gems, we would want a different TMA descriptor for operand A or operand B, etc. This adds some wrinkles to how we will represent TMA descriptors in a group gem. So in a single gem, the way we did this was by constructing our TMA descriptors on host and passing them through to the device kernel through kernel launch parameters. We could consider doing the same for a group gem, but because we have many gems to compute, this could result in constructing many TMA descriptors on host, which would inflate kernel launch parameters. To get around this, CUTLASS's group gem for Hopper makes use of a new feature introduced in CUDA 12.3 that allows us to update fields of TMA descriptors directly on device. Specifically, CUDA 12.3 introduced TensorMap.replace PTX that allows you to update fields like the global address and global stride of a TMA descriptor. The way we use this in a CUTLASS group gem is through the following. First, when we're constructing TMA descriptors, we just construct as many as we would use in a single gem, but these TMA descriptors will be considered just placeholders for now. We pass them through the device kernel through kernel launch parameters, and then in the prologue of the kernel, that is before we perform any TMA copies or MMAs, each CTA will make their own copy of these placeholder descriptors in global memory. Each time that the CTA encounters a different problem in the group, it will use this tensormap.replace PTX to update fields of the TMA descriptors to what will be needed for that gem. And it'll then use these updated TMA descriptors when performing copies. So through this new feature, we're able to directly represent the updates to TMA descriptors that we need on device. We don't need to deal with constructing all these different TMA descriptors on host. Now, as I mentioned, this is just one of the optimizations we've considered for GroupGem. I encourage you to take a look at the code to learn about more of them, and especially to get a better sense of how to use this new feature. So GroupGem has been supported in CUTLASS since version 2.8 for Ampere, and we recently added Hopper GroupGem support as beta in version 3.4. And we plan to continue to optimize it in future releases. GroupGem has already seen some current adoption. TRT-LLM uses it for serving the Mixtral 8x7b model. ByteDance has used it for byte transformer. And PyTorch Geometric has used GroupGem for some primitive operations within it. GroupGem is available via both the C++ and Python interfaces to CUTLASS, and I encourage you to try it out via the following examples. Next, I want to briefly describe how CUTLASS's mixed input gem enables generic weight quantization for large language models. The idea behind weight quantization is simple. We'd like to represent weights via a smaller data type so that we can potentially fit a larger model within a single chip. So what we would like to do is, instead of performing an FP16 weight times FP16 activation matrix multiplication, we would instead like to do int4 weights, for example, times an FP16 activation. We typically refer to this type of operation as a mixed precision gem, mixed input gem, because the data types for matrices A and B are different from one another. Under the hood, the way this will work is by eventually converting the narrow precision weight into the same data type as the wider precision and performing a tensor core instruction within that wider data type. CUTLASS's implementation of mixed input gem enables significant savings in global and shared memory footprint and bandwidth. And this is because the weight remains in the narrow data type in both global and shared memory, and then is only converted to the wide data type within the register file before performing the tensor core MMAs in the wide data type. Under the hood, CUTLASS has a number of optimizations in mixed input gem, including optimized conversion sequences from the narrow to wide data type. Using a mixed input gem in CUTLASS is also straightforward. All you need to change are element A or element B in the collective main loop builder. For example, we could change this FP16 gem, or main loop, into one in which we use int4 for element A via the following small change. Furthermore, CUTLASS's implementation of mixed input gem is generic. It allows for a wide range of narrow and wide data types to be used alongside one another. Either operand A or operand B can be of the narrow data type. All that's needed is that a tensor core instruction exists in the wider data type, and that operands continue to be well aligned for using TMA. This allows you to experiment with mixed input gem ranging from FP16 times int8 all the way down to multiplying a single bit, int1, times an FP8 operand. Mixed input gem was introduced to CUTLASS in version 3.3, with the Hopper version currently being used by TRT-LLM. Support for mixed input gem in Ampere was contributed thanks to Manish Gupta of Google via an open source contribution. We encourage you to try out mixed input gem for yourself via example 55 in the CUTLASS repository, and hope that it can enable you to experiment with generic weight quantization for your workloads. Okay, for this next part of the talk, I want to switch gears and describe how CUTLASS's epilogue visitor tree abstraction enables complex epilogue fusion patterns. So a common workload in many applications is to compute a gem and then to compute some additional operations on the results of the gem. Examples might be a ReLU or adding a bias vector. We typically refer to these extra operations as the epilogue because it typically takes place after the gem has occurred. Being able to fuse epilogues to the kernel computing the gem itself is critical for achieving high performance, because doing so allows us to reuse the results of the gem from faster levels of the memory hierarchy, as well as to avoid any additional kernel launch overhead from running these kernels serially. Unfortunately, writing customized fusions in CUTLASS prior to the abstractions I'm about to describe was a cumbersome process. Doing so typically required one to have significant expertise into CUTLASS's existing optimized epilogue loops so that they could determine where they should place their custom logic. Once one had figured this out, they would then need to make copies of CUTLASS's epilogue and gem files in order to target their new epilogue. Overall, this required hundreds of lines of C++. Making matters worse, this same process would need to be repeated for every additional epilogue that one wished to experiment with. Overall, this led to a slow iteration cycle for trying out new epilogues. To ease this burden, CUTLASS has introduced the epilogue visitor tree, or EVT, abstraction. EVT builds atop a set of primitive compute, or load, compute, and store nodes that are common to many complex epilogues that can be composed together into tree or directed acyclic graph-like structures to allow you to build up higher-level, more complicated epilogues. Taking a simple example at the bottom of this slide, let's consider the basic epilogue that's computed in normal gem. In this epilogue, we take the result of the matrix multiplication, that is the accumulators, multiply it by a scalar alpha, and add to this the result of multiplying scalar beta times an additional source tensor C. This epilogue could be converted into the tree structure on the right via a multiply node that takes in alpha and accumulators, a multiply node that takes in beta and C, and finally an addition node that takes in the results of these multiplications. EVT allows you to build up such fusion patterns via these primitive building blocks, and critically, handles all of the complications of lowering this logic down into CUTLASS's optimized epilogue loops for you so that you can focus on just building up the logic for your epilogue. To give you a better sense of how you can make use of the EVT abstractions, I want to walk through a slightly more complicated example. So in this case, we're going to consider the same epilogue that we saw on the previous slide, but we're going to add to it a bias vector and then compute a ReLU over all of the results. Now, I'm not going to walk through it, but it's fairly straightforward to see how you could convert this epilogue into the tree on the left, in which we have two multiply accumulate nodes and a final ReLU node. OK, we'll next walk through this tree piece by piece. So to start with, we're going to build up the first multiply accumulate node that operates over alpha, accumulators, and bias. We first need to represent how we're going to load each of these operands. For scalars like alpha, we'll use a dedicated SM90 broadcast node. We load the accumulators via a dedicated SM90 accumulator fetch node, which tells us to fetch the accumulators from the register file. Finally, bias vectors can be loaded via SM90 column or row broadcast nodes. We specify the compute operation that we'd like to perform via an SM90 compute node, here tagged with the multiply add operation. And finally, we hook these components together via an SM90 EVT, here specifying that we'd like to compute multiply add over operands alpha, accumulator, and bias. The next multiply add follows pretty similarly. The beta is represented just as we did for alpha. Additional source tensor C is represented via an SM90 source fetch node, which tells us that we'd like to load tiles from global memory. And finally, we hook these together via another SM90 EVT, reusing the multiply add compute node that we saw previously, but this time operating over operands beta, C, and finally over EVT compute 0, which is the EVT that we defined for the previous multiply add. This tells us that we're going to be feeding in the outputs from the first multiply add into the second one. Representing the final node follows pretty straightforward. We declare a new compute node, this time tagged for ReLU, and then hook it up into a final SM90 EVT, this time operating over EVT compute 1, the results of the previous multiply add. This final EVT output contains all of the logic needed to represent our fusion pattern. It can then be used in in a CUTLASS kernel by changing the epilogue output field in the collective epilogue builder. So hopefully this has given you a sense of how you can build up a slightly more complicated epilogue using these primitive building blocks. To make matters a little bit easier for users, CUTLASS also comes with a number of predefined aliases for common epilogues. So for example, the epilogue that we just saw could be more succinctly represented via the two lines at the bottom of this slide. And we have another number of other pre-baked aliases like that. In addition to supporting EVT via the C++ interface to CUTLASS, we also support it via the CUTLASS Python interface. Using EVT in the CUTLASS Python interface is very straightforward. First, you need to declare a basic gem that you would like to compute, specifying at a minimum the element type and layout type for the gem. You next define an epilogue that you'd like to compute via a pure Python function. In this case, we're specifying the same epilogue as was used in the previous example that does ReLU and bias add. This function here is just basic Python. We have a number of convenient helper functions like ReLU for common operations that you might want to perform. You then declare a set of example inputs specifying the shape and type of the operands and outputs of your EVT. And finally, call cutlass.epilogue.trace, passing as inputs the myEpilogue function you defined for your epilogue, as well as the dictionary of these example inputs. Under the hood, this method will parse the Python abstract syntax tree for your myEpilogue function to convert it into an epilogue visitor tree. It will then use the example inputs to propagate type and shape information through the tree, and finally perform some optimizations on the tree, like removing dead nodes. This can then be used in a CUTLASS kernel by calling plan.run. Under the hood, what this does is it emits the C++ corresponding to both the gem and to this EVT, compiles it, and runs it. And overall, we think that the Python interface to CUTLASS enables a pretty easy way to get started both with CUTLASS and to EVT in general. All you really need to do is write pretty simple Python code for your epilogues, and you're ready to get started. So we especially encourage this to you if you're new to either CUTLASS or to C++. Now, I mentioned at the beginning of this talk that EVT handles all of the heavy lifting of placing custom logic within CUTLASS's optimized epilogue loops. On this slide, I want to give you just a taste of what's going on in this. Now, don't worry, I'm going to go through this slide relatively quickly, but I don't want you to need to necessarily read all of it. Really, what I'm trying to get across is what EVT is handling under the hood for you so that you can just focus on building up your epilogue patterns. So the way EVT works is by taking CUTLASS's optimized epilogue loops and adding to it a set of callback functions. These callbacks are placed in strategic locations based off of where one would commonly add custom logic to CUTLASS's epilogues. Each primitive node in EVT will define what it should do when one of these callbacks is reached. When the overall epilogue reaches one of these callback locations, the EVT is traversed, and the corresponding functions for different primitive nodes will be called. This allows us to place the custom logic for your epilogue within CUTLASS's optimized epilogue loops. But again, as an end user, all you need to worry about is building up your fusion pattern via the primitive nodes, and we'll handle all of this under the hood for you. So EVT is currently available in both the C++ and Python interfaces to CUTLASS, with support for Hopper, Ada, and Ampere architectures. Support for sparse gems with EVT was added for Hopper thanks to a contribution from Alexander in open source, and we plan to add support for EVT on Hopper sparse gems in the near future. We encourage you to try it out for yourself via the following two examples and hope that it will enable you to experiment with custom epilogue fusion atop your CUTLASS kernels. And I'll next hand it back off to Vijay for an additional part.
All right, well, I lied to you about the agenda. There's one more thing. One of the most common questions that we get about CUTLASS is, OK, this is fine and all, neat. How do I write a custom kernel? Sometimes even EVD is not enough for you to write something super custom that nobody else has a clue how to write, and EVT cannot support. OK, well, let's walk through how you would use CUTLASS. This is where CUTLASS and Q truly shine. This is when you have domain knowledge about your problem that a compiler or a library cannot understand, and you can go in to optimize something to make full use of the hardware. In this case, I'm going to take the Ampere gather-scatter convolution as an example use case. And this is not something that the CUTLASS team has ever talked about before. So let me motivate the problem statement a little bit. Let's say you have a ton of LiDAR data. The LiDAR data has 3 spatial dimensions, height, width, and depth. And most of it is sparse. Most of it is zeros, because you have a self-driving car scanning a bunch of points in streets. Sky doesn't have any points in it, empty voxels. Then what you want to do is run a convolution kernel with it, where the weights are dense. What that means is I have NDHWs that are sparse, but given that there exists a voxel at that location, I have a dense channel vector. What I would like to do is run a gather-scatter gem, so I don't have to blow up my GPU memory usage and run out of memory. OK, then what I need to do is implement a gather-scatter convolution. How do I do that? That doesn't exist today off the shelf. Well, let's start by defining the kernel API. The first thing you would do for a kernel like this is set up the input parameters and the interface to your kernel with Qt tensors, where, just like I told you about before, the IAM2call transform is presumed to have been applied to the activation tensor so that it's logically consistent in its n, m, and k dimensions to be worthy of to be applied to an implicit gem algorithm. Okay? This is step 0. Now, the real problem is going to be, how do I implement this as a main loop? And then, secondly, how do I represent my Qt tensors to do this gathering and scattering? Let's take the easier case first. Let's write a dense 3D convolution in Ampere, 4 Ampere. Well, we can use the Qt layout algebra to transform the input tensors to the IAM2call domain. And the way we do that, I have omitted the actual Qt algebra over here. That'll be released in a later version of CUTLASS at some point. But you can imagine that the transformed activation layout has a logical shape in M and K as NZPQ and CTRS multimodes. And one thing to remember is every Qt layout is a function from some set of inputs, integers, to some index space, right? So in this case, I'm taking the NZPQ and CTRS and as a function that maps onto the linear index in that tensor. And then I can just take that IAM2call transform tensor and use an off-the-shelf gem collective. Remember, every CUTLASS gem collective is just a tensor contraction in disguise. We just call them gems. But they can deal with these multimode shapes, no problem. And that's it. We have implemented a dense 3D convolution. And what this shows is, if you have some custom kernel that you would like to do a fusion for, you can reuse the CUTLASS collectives as a tile-level program, and then write your custom kernel schedule around it. So how do we do the gathering and scattering? Well, remember again, layouts are just functions. And in this case, we can represent the gathering and scattering as a composed layout of 2 different layouts. What my first layout is going to do is that it's going to take the logical coordinate m, k, and it's going to transform that to a pair of codomain outputs, each of which is going to correspond to my offset in the index buffer for gathering and the dense offset along the channel dimension. Okay, so now this is a layout that doesn't just map onto a single index, but rather the codomain itself has a rank of 2. And the way we do that is by setting up these basis strides, which tell this layout in which rank to accumulate some certain output codomain 2. So in this case, we have 2 domains in the output. The first is the gather basis, which is going to be the codomain 0, rank 0, and then codomain rank 1 is going to be the contiguous bases in the offset channel dimension. And then what we do is we set up another layout that's going to have these 2 outputs of the first layout as its domain, which then maps onto the linear index within the tightly packed gather tensor. And that's what that looks like. The custom stride comes from example 51 that we published in CUTLASS a long time ago, which was the Hopper gather scatter input gem. But we are reusing that over here for this convolution example. And then that's it. You set up a composed layout of these 2. So the domain of this layout is logically consistent with my m, k convolution, IAM2call. And its output is going to correspond to my compressed memory for this sparse activation tensor. And you can imagine this scattering is a symmetric layout. There's no difference between gather and scatter when we talk about the layout mapping itself. And that's it. Nothing else really changes. Once I've represented my tensor like this, all I have to do is dispatch to the exact same collective. Not a single line of code changed within the pre-tuned CUTLASS recipe. And that's the entire kernel code over here represented within 63 lines that achieves peak performance on Ampere hardware. Awesome. You can try this on example 59 in CUTLASS 3.5, but there are some other excellent examples of custom kernels written using CUTLASS, including TreeDAO's Flash Intention v2 and Colfax's extension to it to adopt Flash FP8. And in conclusion, that's CUTLASS. CUTLASS 3.5 is out today, and it's continuing to provide abstractions for writing custom kernels for your DL and HPC use cases. If you need help or you have feature requests or bug reports, please file an issue on GitHub or reach out to our excellent product manager, Matthew Nicely. With that, I'll leave you with our roadmap slide, as well as a lot of gratitude for our community and large users for continuing to support us, continuing to use our library. And for a full list of contributors, please check out our GitHub for the contributors page. Thank you.
Thank you, Vijay and Jack. Excellent talk. And thank you for CUTLASS. We use it heavily in CUTLASS, which is in my team. So I'm sure we have some questions. Who wants to get us started? I'll hand the microphone over. Questions?
Hi, I'm Daniel. I want to know if you could do, I believe you call it mixed precision gem, where you do like in4 weights, FP16 activations. Can you do that with sparse weight matrices as well? Can you combine the two?
We don't currently have support for that.
Do you think it's something that can be done, or?
We have some of the experts of mixed input gem in this
Oh, yeah.
room.
Yeah, let's get you in touch with Ron after the session, and then we can chat.
One question on the convolution.
Yes.
I'm just thinking out loud, can we do 6D with TMA? Like you said, we 3D, we do 4D, 5D, 6D, without having a bounds check manually. Like TMA can check five dimensions, right?
Yeah, so the way we would support that is through the multi-mode tensor contraction ways that we do for tiled mode TMA. You can talk to Chris later on, but we believe it's possible to do for arbitrary dimensional convolutions as well. But it's not something we have stamped out a kernel for and tried yet.
I know
But
it's not needed, but
hunch says we can do it.
okay.
Yeah.
And then one of the slide, I think you said like you can do int 4 or int 6 and then mix input. It's a small thing I observed. I think we also need to change the operator tag to
Mixed input. It's not checked for CUTLASS 3 API, but it is checked for CUTLASS 2.
Okay.
Yes, that's right. Of course.
Thanks for the sharing. Any awesome fundamental changes for Blackwell? For the B?
No comments on Blackwell at this time. Sorry.
Okay.
You can talk to Matthew nicely if you would like details on the roadmap and stuff.
Non-Blackwell questions, please.
My question is on the last example that you're trying to do a different layout. What's the impact of or implications of that on the TMA? I mean, do I need to care about the performance-wise?
I see. So the last example that I showed, are you referring to the gather scatter example?
Yes, yes.
We do not use TMA for that one. So that is an Ampere convolution, and it cannot have TMA instructions because Ampere did not support it. So that one is still using the CPA sync or LDGSTS instruction to implement copies.
So what would be the ones, the hardware with the TMAs that do you plan to use that, or it's?
Oh, this is just an example kernel. We can consider, if you have a use case for gather scatter convolutions on Hopper, come talk to us and we can try to put that into our roadmap. Yeah.
Is FP8 group gem available?
Is FP8 group gem available? I think we have.
It should just work.
Yeah, I think it should just work. I don't know off the top of my head whether we stamp that out right now, but there's nothing I can think of that would preclude the use of that.
Sorry, I'm the author of the Colfax version of LLM. So one of the difficulty we face is shipping the library with a lot of template parameters and auto-tuned parameters. So do you have any solution for that? How do you ship a CUTLASS-based library?
Yeah, so in general, there's no general recommendation we give for tuning these template parameters. It's usually specialized for the problem and the kernel that you're implementing. What I would recommend is starting off from the CUTLASS profiler setting of these template parameters and seeing which ones perform best. It's very easy to get an excellent starting point for these template parameters if you look at the Hopper and Ampere profiler settings for the tile shapes, etc. We really do a lot of work in tuning these tile shapes and how the kernels are scheduled so that the configurations we ship in profiler are as close to optimal as possible. And then what we recommend to our users is come talk to us either through our Discord or issues or discussions on GitHub or email Matthew nicely, and then we can help you optimize them even more.
I can do a plug for my own talk tomorrow. We will actually show Python APIs where you can query what heuristics CUTLASS is recommending, and you can use those in your CUTLASS kernel. We have AI-based heuristics. Yeah, the details are tomorrow. So that was the plug.
Hey, I had a question about the EVT. I saw there's a column and row reductions. And how do they work? Like, is it possible to like implement an epilogue that takes 4 values in a row and combines them into one, for example?
And combines them into one. Most of our reductions take place across, for example, like an entire row or an entire column. So if the 4 you're referring to there is one of those dimensions, it would be yes, but could you give a little more information what you mean?
So what I want to implement is an LSTM. So basically there's 4 values.
Mm-hmm.
There will be, I need to do different operations on them, or like 3 are tonnage, 1 is a sigmoid, and then combine the 4 into one value, and then I write out only the one value.
Mm-hmm. Okay, so is this like an overall reduction? For example, like you had your 4 inputs was the entire tensor. Is that what you're saying, or 4 values?
No, so you could imagine that like there's an inner dimension that's 4, and I want like it's a 3-dimensional output basically, and I just want to get rid of that last dimension by combining the 4 values.
Okay, I mean, yeah, we do support generic row or column reductions. I can't tell if that's what you're talking about, though, for reducing that final dimension.
I guess I found that so far I just wasn't able to use the epilogue concept for that, so I had to kind of just write custom kernels that don't use epilogues at all and access the accumulator tiles directly.
Okay, why don't we talk offline afterwards
Yeah.
to better sync up on what you're trying to do. Yeah.
Other questions?
So your examples for customizing at the end were for Ampere. I think when you go to Hopper, when you start doing it inside your own kernel, you lose things like persistent, asynchronous, you lose the TMA and so on. Is there anything you can do to mitigate that? And if you can advise on how bad it is in your experience?
Mitigate what exactly?
Like how much performance should we expect to lose from that? And is there anything we can do that would make, for example, the main advantage of TMA is better latency tolerance, especially persistent groups as well.
Yeah.
Is there anything you structure it? I guess the obvious thing would be, example, make sure your register pressure isn't too bad in the rest of your kernel. I don't know if you got any other advice of that kind.
Do you have an answer for off the shelf?
Off the shelf for
Do you have an answer? I don't know if I understand the problem statement quite well.
Basically, there's some efficiency you lose when you do use kernel level rather than device level.
Yes.
And is there
I see
anything
what you
you can
mean.
do to mitigate
That's
that?
right. Yeah. So it depends on which level of the hierarchy you're using, right? Like what we try to do is, in isolation, every single component of CUTLASS is as optimal in the hardware as possible. So in the custom example that I showed you, the collective is known to have optimal efficiency. But as you say, if your kernel is not orchestrating that collective in the right way, you can lose efficiency over there. And are you asking how to mitigate those losses over there?
Yeah, especially for Hopper, because there's a bunch
Yeah.
of things we lose that are not relevant to Ampere.
That's right. So, so Ampere also had persistent kernels implemented, especially in the group gem case. So specifically for this example, we could implement stream K as well as persistence for Ampere kernel, and that would work decently well across Hopper, but be optimal on Ampere still. So the answer to your question really depends on which component of CUTLASS you're using and in what context of the kernel, and what the bottlenecks are. So it depends on what the NSYS profile says and things like that. But generally speaking, the ways to optimize would be just make sure you're optimal at the local level, and that local level composes well with the rest of the structures, and that gets you 90% of the way for the most part.
Thank you.
Mm-hmm.
So I noticed that you have this example 53 in Hopper with the gem with an permute operation fused to the epilogue.
That's
is
right.
that supported in the EVT? And is that...
No. I believe we do not support permutes in the EVT today.
Okay.
Yeah.
Is that planned? Or?
Good question.
I'm not sure that it's... I think you would have to consult Matthew Nicely about the specific roadmap for that.
I am not aware of a EVT productization for permutes, mainly because it's difficult to support permutes via TMA natively.
Right.
So we would have to come up with ways to effectively implement that across, and probably implement CP async-based collective epilogues as well. So if you have a pressing need for it, email your use case and requirements to Matthew Nicely, and we'll take it from there.
Thank you, Vijay and Jack, for a great talk and lively Q&A. Please join me in thanking them one more time.
Thank you so much for attending.